Okay, so why doesn't correlation imply causation? Of course, one of the mantras of every statistics teacher is this: correlation does not imply causation. But why not? Actually, it's pretty straightforward. So after I answer that one, I'm going to address two bonus questions in this video. What statistic does imply causation? And can correlation ever be used to test a causal theory? All right, so moving on. So, if I measure two variables, like ice cream sales and drowning deaths on days, or hours spent playing violent video games, and the number of shocks that a person will give to another person in a game, in a learning game, in a psychology experiment, or whatever two variables you want to think about, we'll just generically label them X and Y. There are only a few different relationships that these two variables can have with each other. So first, and always the most likely one, here let me turn on my laser pointer so I can laser point, there we go. Always the most likely one, if we don't know anything about these two variables, is this one, that they have no relationship to each other. Now I've just used the not equals symbol here to stand in for that, but it means X has nothing to do with Y. They are not related, they're not the same thing. Okay. It might be the case that X causes Y, and we represent that with a directional arrow, an arrow pointed from X to Y, to say X is a cause of Y. Or it could be the case that Y is a cause of X, and there's, of course, the possibility that a third variable Z causes both X and Y. And there is actually one more potential relationship between them, and that is the mediated relationship, that X causes a third variable Z, which in turn causes Y. But we can ignore that one because you notice that it's still the case that X causes Y. It's just that X is what scientists call a distal cause, whereas that third variable Z right here is what scientists call a proximal cause. So X here, a more distal cause of Y, Z is a more proximal cause of Y. But X is still causing Y here. So we're just going to fold this one into the X causes Y relationship, and we can ignore it for purposes of this argument. So when we find a correlation between X and Y, why can't I just conclude that X causes Y? Well, it's because the correlation by itself only eliminates one of these possible relationships, and the correlation is consistent with all of the other relationships. And of course, the one it eliminates is that one right there. So once we find a correlation between X and Y, we know that the relationship between them is not this one. It's not no relationship, but we don't know which of these three it is. The correlation is equally consistent with all three of these possible relationships. And of course, this one right here, the third variable causing both, is probably the most likely one. Again, if we don't already know a lot about X and Y, then the most likely situation is that there's some third variable we don't know about that's causing both X and Y. And usually those relationships are not terribly interesting. They can be funny, though, as demonstrated here on this website. So I'm going to just put this link in. I'll put this link in the description of the video below as well, because it's just kind of a funny website to go to. They've got really funny correlations between things like, how much money Wisconsin spent on cheese, and what team won the Super Bowl championship. That kind of weird stuff. It's kind of funny, but it just goes to illustrate really well why we can't infer cause from a correlation. And the trick that this website uses is actually just to find variables that change over time. So if you find any two variables that change over time, and then you figure out what time points you want to look at, what span of time you want to look at, you can always find a span of time where the two of them appear to be changing together, either positively or negatively. When one goes up, the other goes up, or when one goes up, the other goes down. And so you can just find correlation between basically any two variables you want, as long as both of those variables change in time. So it's kind of funny. All right, so back to our example. The favorite example of a lot of stats people just really easily illustrates this is the ice cream and drowning deaths. So the money spent on ice cream each day is positively correlated with the number of people who drowned on a given day. The more money spent on ice cream, the more people are going to drown. So should we advise people not to eat ice cream before swimming? Well, of course not. The ice cream is not the cause of the drowning. There's a third variable, right, which is temperature. The higher the temperature, the more ice cream people eat, and the higher the temperature, the more people go swimming, and swimming, of course, is when they drown. You can also drown by slipping in a bathtub, which is not necessarily weather dependent, but just when the weather gets hotter, more people are swimming, more people are swimming, more people are drowning. So there is a third variable that causes both ice cream consumption and drowning. Ice cream and drowning themselves don't have anything to do with each other. All right, so that brings us to our first bonus question. What statistic then does allow us to infer that X is a cause of Y? Well, it turns out that no statistic allows us to infer cause. And to understand why that is, you need to know how we do infer that X causes Y. And to do that, we have to establish three things about the relationship between X and Y. And here they are. So, the first criterion is covariation. We need to establish that as X changes, Y also changes. And that's exactly what the correlation establishes. Then we also need to establish temporal precedence, that the change in X comes before the change in Y. And the reason for that is the physical law of entropy. You can't have a cause after its effect. And three, internal validity, meaning that no third variable can explain the covariation between X and Y. Statistics can really only help us with that first criterion. Whether it be the correlation, a t-test, an f-test, chi-square tests, all of them serve to establish covariation. Or they can, of course, fail to demonstrate covariation. But covariation is really all that statistics deals with. Now, okay, there might be some times when statistics is necessary to determine temporal precedence, when there is mush in our measure of when things happen. And of course, by mush, the technical term I mean there is measurement error. But generally, temporal precedence is established by either the time of the measurement itself or by experimental design. Which brings us to internal validity. How do we make sure there are no third variables? Well, to do that, we have to run a controlled experiment where we use things like random assignment to conditions and blinding to ensure that there are no potential third variables except for chance. Now, we can never get rid of pure chance as a third variable, but that's what the p-value is all about in null hypothesis significance testing. That p-value is the probability of getting our result if it was caused purely by chance. All right, so that brings me to our next bonus question, our last topic. Correlation does not imply causation, but can it ever be used to test a causal theory? Now, I used to think no. I thought correlation was pretty useless. I wanted to know what things caused other things to happen, and I wasn't interested in mere correlation. But I got to thinking, what is necessary for a test of a causal theory? The person who figured out the most popular way of figuring out if something is science or BS, and of course we all know what BS is, right? BS is bad science, was a philosopher named Karl Popper. Great name. I really wish my name was Popper. Anyway, Popper was contemplating the difference between Sigmund Freud and Albert Einstein, and why everyone agreed that Einstein was a great scientist, but lots of folks thought Freud was a fraud. And Popper figured out that it was because Einstein's theory made predictions that might be false. In fact, lots of physicists thought they were certainly false when Einstein first proposed his two theories of relativity, the theory of general and special relativity. A lot of physicists at the time thought he was completely nuts. But Freud's theories didn't make any predictions beforehand. Instead, they could explain anything after the fact. They didn't forbid any behavior. They didn't forbid anything from happening. Whereas Einstein's theories said that lots of stuff could never ever happen. No way, no siree. So this led to the falsifiability criterion, the idea that a theory is scientific if it could be falsified by a plausible observation. Something that we might see that is not absurd to contemplate beforehand. Which leads to the idea of what it means to test a theory. A study is a test of a theory if and only if a plausible outcome of the study would refute the theory. Which brings us back to correlation. If a theory makes a prediction that a correlation should exist in the population, and whether the correlation is positive or negative, we have to have that direction, because otherwise we're betting against the null hypothesis, and then we get rewarded for having high measurement error. So we can never bet in favor of the null. But so if the theory predicts a correlation should exist and whether it's positive or negative, then we could measure those variables, estimate the correlation, and if the correlation came out like the theory predicted, that would be support for the causal theory. Now, it's support for the causal theory if and only if a correlation in the opposite direction is plausible before we measure the variables, and if such a correlation would refute the theory. So this can't be a correlation we already know exists, because that's post hoc. That's after the fact. The horses have already left the barn. In fact, that's pretty much like betting on a horse race after it's over and you know the winner. Who would do that? Well, actually, anybody would do that if they let you, right? They don't let you place bets on horse races after the race is run and you already know the winner. For the exact same reason that a correlation that we already know exists is not evidence for or against a theory that was meant to explain that correlation. But if the theory predicts a new correlation, one that we have not yet observed, and if a correlation in the opposite direction would refute the theory, then observing that correlation supports the theory, even if the theory is a causal theory. Alright, so summing up, correlation does not imply causation because it does not rule out most of the possible relationships between the variables. No statistic, it turns out, implies causation. Instead, number 3, the inference of cause is enabled by experimental design. But, having said all that, correlation can be used to validly test and hence support a causal theory if the theory predicts a previously unobserved correlation, and a correlation in the opposite direction, which has to be plausible beforehand, would refute the theory if it were observed. So in that case, a correlation can validly support a causal theory, even though the inference of cause itself cannot be supported by the correlation by itself. Okay, and I think that's enough.